what you have all been waiting for, and that is chemistry, physical science with John. How are you, John?
I'm doing great. Thanks, Katlego. Great to be with you guys, and it's my favorite as well.
That's it.
Chemistry, we're dealing with chemical change today.
Okay, awesome. That's what Spring School is all about. We deal with everything under the sun. So let us know what we'll be going through today.
Okay, Katlego, we've started by looking at rates of reaction earlier on and chemical equilibrium. We'll touch on that again. If you've got more questions on either rates or chemical equilibrium, I've seen a couple on the page already, so we'll tackle some of those. And we'll also look at the other aspect of chemical change, which is on the redox reactions and on electrochemistry.
Oh, wow.
So we've got a lot in store.
So we've got a lot in store. Hey, that's great, John.
But I'd love to hear from the learners. I'd love to get them responding.
Yes.
I know there are some sections here that give people nightmares. It's those KC calculations. Today I want to sort those out.
That'll be
I want
awesome.
to put them into perspective. Make sure that after today, it's not going to be a worry. It's going to be something that you know you can calmly take and ace forever.
That'll be awesome, John. Thank you.
Okay, well, shall we go and look at the competition question?
Let's go look at the competition question. Do you
Okay.
want to look at it now before I tell them?
Yeah, let's go.
Okay, go right into it.
Okay, so here we go. It's about our favorite topic in this section. It's about KC. But this time it's not a KC calculation. What does it say? It says the KC value increases when the temperature of the container increases. What can you deduce about the reaction from this information? And you're given three choices. The choices are A, fewer products are formed at higher temperature, the reverse reaction is favored, or C, the forward reaction is favored. Guys, remember the code is 1673. Kat, how can they enter?
Thank you, John. Guys, you know already what the drill is, but I'm going to remind you because this is such an important part of the show. You can enter through many avenues. There's our email, which is win@learnextra. There's the Facebook page, which you're all familiar with, facebook.com/learnextra. There is pep text, where our group code is learnextra. And also there's SMS, guys. Please send us SMSs. Our SMS number is 083 448 8810. That's 083 448 8810. On our Facebook page, make sure that you add the group code on top or underneath. You enter on the events page, guys. If you look on the events page now, there is the competition question. There is where you can enter. It gives you all the instructions. And when you enter through SMS and email and pep text, you always add your name. Remember that your name is very important so that we know who we're dealing with. And if you win, then we know exactly who to announce. John, do you have anything to say?
Yeah, Kat, just to say that I put up on the main page, because some of the guys didn't have phones that could get to the events page. So on the main page, there's the question as well. But please post it below the picture of the question as well.
So
on
not,
the main,
not randomly on the page. Don't send us an inbox message either. On the actual page, there's the post, and there you answer underneath that specific post. Not on the greetings post, on that specific post. And in the events page. So you guys already know how to deal with this. So I'm just reminding you, just as a matter of formality. Also, there's some awesome prizes, guys.
Yeah, tell us about those.
I know, I love those. There's the 3 CDs. Today we have Lection Gentlemen's Club. We have Electro Candy 4, which is a Soul Candy CD, and we have the Mikasa Platinum Edition, which is also a Soul Candy CD. Also in store for you today, we have our physical science study notes. Now, these are very important, guys. Get your hand on this book because it's gonna be such a breeze to write these exams. Also, we have the t-shirt, and it's like the one I am wearing, this really awesome bright blue t-shirt. So make sure that you are the winner today. Guys, enter as many times as you like. As you saw, people are even giving you advice. Guys, you forgot to add the code, or put it on the events page, or help each other out and keep helping each other because it's such an important thing. Also, remember to concentrate this show, guys, because it's so important to get through all your stuff and all your revision for this year. I know that you guys have many questions. If you've been watching the whole morning, you already know that I have questions. So post them through right now because John is here to answer them. Thank you again to Liberty for bringing us such a fantastic show.
Absolutely. Kat, thank you so much. Guys, maybe you're wondering why I'm wearing this funny t-shirt. I don't always wear it, but guys, I'm not supporting a particular sport team today. It's not for the cricketers, it's not for the football players or for the Olympians, it's for the class of 2012. I'm right behind you. I want you to do the very best you can, and I'm going to try and help you do that by making sure that you've got it buttoned up. So how are we going to do it? We're going to start by looking at the February-March paper from this year, the 2012 paper, and I want to work through some multiple choice questions to start with. Now, don't forget the multiple choice. Some people say, they're only 2 marks each. Yeah, but there are enough of them to carry quite a bit of marks altogether. So, 20 marks out of 150, it makes up, adds up. Make sure you practice your multiple choice. Make sure you practice your short questions. We don't always get time to do that, so let's go to those short questions, do some revision. Come with me. Let's go. First one. So here we go. 2.5. It says the following. The diagram below shows the change in potential energy for a hypothetical reaction representing by the following equation. So let's just recognize that we've got a hypothetical reaction. There's the equation. X2 as a gas plus 3y2 as a gas produces 2xy3 all as a gas. And so they've balanced the equation. We checked that it's balanced. They've then given us this lovely diagram, and we need to be able to interpret it. We recognize we've got potential energy in kilojoules here. This is the reaction coordinate, and you should recognize straight away what we're dealing with here. This is what I like to refer to as an energy profile. When you get one of these, in your head you need to start thinking, what am I being told about the reactants? What am I being told about the products? What am I told about the type of reaction? Let's just go back and make sure that we've got that all sorted out. Remember the things that we start with. These are called your reactants. Okay? Those things on the left-hand side of the equations, those are your reactants. The things on the right-hand side are your products. That's what's being formed in the reaction. Now, what we recognize from this diagram is that we've got our reactants here. And so we know what the energy of the reactants are, and that's a product. So we are given a comparison of the energy of the reactants compared to the energy of the product. Now, have a look at what it's saying to us. It's clearly indicating that the energy of the reactants over here is higher than the energy of the product. So more energy is released than what was put in. That was the energy that was put in. We know that that's got a special name. It's called the activation energy. We also know that that point there is known as the activation complex. So this is where the reactants meet together and they form an unstable intermediate, which can then fall apart to form the reactants again, or it can produce the products. Let's go on to the question and see what it says. It says, the activation energy for the forward reaction. Now, in this case, there was only a forward reaction. It didn't say that it was reversible, but recognize from the diagram that reading from left to right is the forward reaction. Starting with the reactants, ending with products is the forward reaction. So, what we have to do is to say, the activation energy for the forward reaction is. So I'm not even going to go and look at the options now. I'm going to look at the graph. Go back to the graph and calculate it. I'm not going to guess. I'm going to do the actual calculation. So guys, have a look. I want EA. It's the difference between these two lines here. What do I know? I know, and I've just smudged it up, so I want to just erase it. I know that the total amount of energy released from the activation complex down to the product is 180 kilojoules. So that was the energy released. Let's just rewrite it. released 180 kilojoules of energy was released in the reaction. But what are we told about this number here? Notice this is the difference between the reactants and the products. You should recognize that's delta H. Delta H is the heat of reaction or the enthalpy. It tells us how much there is a difference between the product and the reactant. Remember, delta H is very important because it describes to us whether the reaction is endothermic or exothermic, and you need to know that. So what are we told here? The difference is 80. So I know that delta H is equal to positive 80. So automatically I recognize that this is an endothermic reaction. So what are we told? We're told energy released is 80. The difference is that one, energy released was 180. Delta H is 80. So I think it's quite straightforward to say that, well, that one must add up to 180. So that one must be 100 kilojoules. That's the activation energy. So where do we go? Go to the solution, go and check what the possible answers are, and there you've got it, 100. Guys, before we speed on to the next question, I do want to just mention something to you that I think is very important just to wrap up energy profiles. What other type of question they can ask you? We've said what the activation energy of the forward reaction is, but what happens if they asked you for the activation energy of the reverse reaction? Well, the activation of the reverse reaction would be that. It would be 180. And the energy given off would be that. So remember the forward reaction here, the forward reaction, you should be able to identify delta H is greater than 0, so we know that it is endothermic. But the reverse reaction, if we were to rewrite this in the opposite way, then delta H would be negative and it would be exothermic. So please remember that theory. Don't forget it. I know it's a revision of grade 11, but it's really important that you know it and you know how to apply it as well. Let's do the next one. I think we've got time for this one because I think it's quite straightforward. So here we go. We're told another hypothetical reaction reaches equilibrium in a closed container at a certain temperature. Here it is, X2 gas, Y2 gas, 2XY this time, and we're told delta H is negative, less than 0. Notice which way the crocodile is pointing. The mouth of the crocodile is pointing to snap at the 0 because it wants the 0, not the delta H. Okay? In this case, the delta H would be on the smaller side. That's how I remember it. I sometimes forget what less than and greater is, and I've got to think about it in terms of the crocodile. So recognize that this symbol is a less than symbol, that the 0 is bigger. That means that this is negative. If it's negative, then it is exothermic. Hope you can see all those links. It's really important that you tie that together. Delta H, less than 0, exothermic. We've got that. Now, we're going to apply it. Which one of the following changes will increase the amount of XY? So we recognize it's in equilibrium, and we want to favor the forward reaction. So we want to push, use Le Chatelier's principle, to favor the forward reaction. They give us the options of increasing or decreasing temperature or increasing or decreasing pressure. Let's deal with pressure first of all. You want to go through this particular case. You've only got two factors to consider, temperature or pressure. I'm going to try and eliminate some. So I just chose pressure so that we can talk about it and make sure that we're right. Remember, when we deal with pressure, we look at the total volume, molar volume. How many molar volumes do we have in the reactant side of the equation? Well, there's 1 mole, and there's 1 mole. And over here, we've got 2 moles. So guys, when you've got a situation like this, where there is no advantage, 2 moles of reactant, 2 moles of product, you're not going to find a situation where a smaller number of moles is favored. They're the same. If we favor the forward reaction, we still have 2 moles. If we favor the reverse reaction, still 2 moles. So pressure is not going to have any effect. So immediately I can ignore those. So I've now got to decide what the effect of temperature is. And for that, I've got to just remember something. An increase in temperature, remember we said we're going to increase the temperature. What does it favor? It always favors the endothermic reaction. Why? Because when you increase the temperature, Le Chatelier says, the reaction is going to the system is want to absorb that increase in temperature. Okay? So it will always favor the endothermic system. So if you increase the temperature, it's going to favor the endothermic. Decrease the temperature will favor the exothermic. Decrease goes with exo. Okay? And so if we go back to the question now, we've recognized the forward reaction is exothermic. So decrease in temperature will favor the exothermic reaction, and we've got it sorted out. But guys, there's a little caveat here. The temperature mustn't go too low. That if it drops below the activation energy, then we've got a problem. But the correct answer here was decrease in temperature. Hope you've got that. Katlego?
Thank you, John. Guys, we're going to go for a really quick break. Remember that during the break, so don't leave your seats, the competition question will be posted. So make sure that you jot it down in case you missed it at the start of the show. See you right after this short break. Welcome back, Mindsetters. In case you have just joined us, we are doing chemistry for grade 12 spring school. It has been awesome so far, and I know that you guys are getting so much in because these are really important. And jot down the answers, because later on when you go through these alone, you already know the explanation and how to go through it. So keep alert, guys, because this is so important. This helps you so much. I know that your finals will be a breeze after the show because really, John, we are here for them fully, right?
Absolutely, Katlego. Thank you. Guys, I want to deal with something that I've seen that some of you have been commenting. You're still battling with chemical equilibrium. And I said at the beginning of the show, I want to sort this chemical equilibrium KC calculation type question out once and for all. So for all of you guys out there watching, let's deal with it. We're going to deal with it by going through the February-March paper, and the question that deals with this particular topic is question number 7. So let's go and have a look at it. So here we go. We're given some background information. We're told sulfuric acid is an important substance used in manufacturing of fertilizers. See how they're bringing different sections together, fertilizers as well as chemical change. And that can happen. The examiners like to do that. The reaction below represents one of the steps in the industrial preparation of sulfuric acid. And they give you the equation, balanced equation, tell you that delta H is negative. Hope you've got that. Remember, that means it's exothermic. Just very quickly to remind you, exothermic means that more energy is given out than is taken in. That more energy is released than is absorbed. Where an endothermic reaction, more energy is absorbed and less is given out. I hope that answers somebody's question out there. So, write down the name of the process. Well, we know that this is the contact process. I'll just quickly go through these in case you want to take a look. And then here, they give you a very important instruction. Write down the name or formula of the catalyst in the question previously. So the formula is it's V2O5. The name is vanadium pentoxide. Now, when they give you a choice of name or formula, that's really up to you. You don't necessarily have to do both. It's either one or the other. I prefer to write down the formula because I don't make the spelling mistake, and maybe that's not a bad thing. Right, let's go to the next part of the question. It says, is the forward reaction exothermic or endothermic, and give a reason for your answer? Well, we've already said that it is exothermic, and the reason is that delta H is less than 0. Or you could say delta H is negative. What that means is that the energy of the products is less than the energy of the reactants. Right. Write down the name or formula of the fertilizer formed when sulfuric acid reacts with ammonia. So, guys, it's ammonium sulfate. Sulfuric acid will always produce sulfates. Formula, ammonium NH4, valency is +1, and sulfate is SO4, but the valency here is -2. So we're going to need 2 of the ammoniums, put them in brackets, and write down the correct formula. Okay, now that was the beginning question. Those were the easy marks. Those were straightforward bookwork, basic chemistry. Let's move on to the real crux of the question, because this is the part that I like, and I think it's the one that you really want to get some help with. It says, the reaction represented by the equation reaches equilibrium at a certain temperature in a 2 decimeter cubed closed container. On analysis, the equilibrium mixture is found that we have 0,6 moles of SO2, 0,5 moles of O2, and 0,4 moles of SO3 in the container. List 3 changes that can be made to this equilibrium to increase the yield. We want to increase the yield of SO3. So, Le Chatelier is what we're looking at. Remember what Le Chatelier said. He said that if you've got a system in equilibrium, you create a stress, the system will work to relieve the stress. Okay, so what are the 3 things that we're going to look at? Well, we want to get more of this. That means that we want to favor the forward reaction. How are we going to get the forward reaction working faster, increasing the rate of the forward reaction? Well, we can increase the concentration of either SO2 or O2. So I'm going to write down increase the concentration, and I'm going to use square brackets, O2 or concentration of SO2. Now, guys, please don't think that you can do that as 2 reasons. You must write either increase O2 or increase SO2. They're not separate. What's another possibility that we can do? Well, have a look again at the equation. We know that concentration affects rate. What else affects rate? Think about it. Well, temperature affects rate. That's right. So how can we apply a temperature change that's going to favor the forward reaction? We just did that in the previous multiple choice question. Remember that because it's the forward reaction is exothermic, we would have to decrease the temperature to increase the yield, increase the amount of SO3. So decrease the temperature, but I'm going to say only slightly. Not a lot, because we don't want the reaction to stop. If you increase it a lot, it's going to stop the reaction altogether. Now, what's the other way that we can do it? Have a look carefully at the volumes that we have here. We have 2 moles and 1 mole. That's 3 volumes in total, 3 molar volumes. And we've only got 2 volumes over here. Ideal. Great. So where is the favorable situation? A low pressure or a high pressure? We want to get 2 volumes. Only 2 volumes. We want to get 2 volumes. Do they want to spread out, or do they want to be packed together? Well, if we have them packed together, then it will force the equation to compensate and allow those two volumes to exist on their own. So by increasing the pressure, we will do exactly what we wanted to do. So we increase the pressure, and that will force us to go and produce more of these things. There is one thing that you might have said, but it would need some explanation. What would happen if you added a catalyst? Well, it's not going to change the actual output of SO3. It's going to change the amount of energy that's required to get there. So in a certain amount of time, we would produce more SO3. But there is something that we can do with that. We can look at another alternative. Because, guys, apart from in industry, if we were to add a catalyst, and the reason we add a catalyst is we want to make more of this, but what does industry do? They remove the SO3. And if they remove the SO3, that will decrease the concentration. If they remove it continuously, they will actually be making more of it. So that's exactly what we would say. We wouldn't say add a catalyst. Catalyst is going to help efficiencies within the production team. But in this sense, what we would do is we would remove, let's just get the pen writing, instead of rubbing out, we would remove SO3 continually. And the more you remove, the more will be made, particularly if you've got a catalytic situation where you don't want the catalysts to get clogged up. By removing the SO3, you're making more space for more reactions to take place. So those are those answers. Right, let's prepare ourselves for the big one. Now, the reason I've done all the other previous questions is because you'll see that this question is for 8 marks. Now, there is so much stress when you see calculate the equilibrium constant that I just want to diffuse that stress and say to you guys, it's 8 marks. It's not worth spending longer than 10 or 12 minutes on. Please do not spend more time on it than is absolutely necessary. The second thing is that there are marks given in this particular set out of this type of problem that are part marks. So it's not an 8 all or nothing. You can always get marks, but I know some of you struggle to get the final question. So the first thing that you do when you see calculate the equilibrium expression, you must write down the Kc expression. So we take a look again at the balanced chemical equation, recognize that's a product, and these are the reactants. And you will know that the Kc expression, we have the products on the top. So it must be the concentration of SO3. And when you look at the balanced equation, what you'll recognize is there's a 2 in front of that. So we must write the square. So we're going to say SO3 squared. The reactants were SO2 and oxygen. Now, this is an all or nothing, so check the equation again, and you'll recognize there's a 2 in front of there, and there's an invisible 1 in front of there. So I must square the concentration of SO2, and I'm going to put the number in over there. So there, by just putting that down, we've already got 1 mark. Make sure that you put this expression down. You don't put the general algebraic one which says A to the A and B to the B. No, we don't want that. We want the simple one for the context that we're dealing with. We don't want it written out in product over reactants. No, we don't want that. It's not going to give you any marks. You can use it as a memory tool to remember that products over reactants, P before R, fine. Remember it. Get it right. But write the full equation down. So that's the first thing. Before you do anything else, before you go to calculations, write down what we were given. You can write that down straight away. Notice I haven't even processed what we were given. So now what it says the temperature is now changed from the original situation and increased. So we know it's increased. We'll talk about what we expect. The reaction is allowed to reach equilibrium for the second time at a new temperature. On analysis, at the new equilibrium mixture is found that 0.2 moles of SO3 is present in the container. Right. So, guys, what we've got to do is we've got to collect our information. We're going to write down what we've been given to start with. In this case, we notice that everything has been given in moles, which is great. Be careful. They don't always do that. The examiners have a sneaky trick of sometimes giving it to you in grams, sometimes giving it to you in concentration, but giving you different things. Some of them in moles, some of them in grams, some in concentration. The examiner was very kind here. Gave you everything in moles. So let's organize our information, and the way I like to organize the information in this sort of thing is to write down in the table method. So I'm going to do it in the table method, and I start by writing the reaction down. I'm going to say SO2, balanced equation, SO2 plus O2 is in chemical equilibrium with 2 SO3. And there's my first step in the table. Check that I've copied it down correctly from what was given. Yes, I have got it. It's the same one that I've written down. So do that check for yourself. Then the next thing is we're going to say ratio. And we're going to write down the ratio. I'm going to use a different color. I'm going to say 2 is to 1 is to 2. Now, guys, this is where you really need to pay attention. It's on the ratio. The ratio is all important. And if you've got to go and get somebody to teach you ratio, do that. Because if you know ratios, you can do this problem. If you're struggling with ratios, you're going to battle all the time. But that's not the chemistry, that's the maths. So my suggestion to you is if you don't know what's happening, find somebody to help you learn about ratios and do it. I will try my best to give it to you now as well. So initial, we're just going to write down all the initial moles that we were given. And then the second line after the initial moles, we're going to say change. We're going to leave that blank, and then we're going to say equilibrium. And we're going to make it clear that we're dealing with moles. Okay. Now, Katlego, I think it's time to take a break. Okay. What I'm going to do is while we have a break, I'm going to fill in the table. And so when we get back, we'll go straight on with it.
Okay, perfect. That would be great. In the break, you guys can also just do some work. Also, clarify what questions you need to ask us, because any time is the right time to ask it, guys. See you right after the break. Welcome back, Mindsetters. Just a quick reminder, don't answer the competition question that is on the actual page next to the comment. Answer it underneath the post. Also answer on the events page. It might be easier that way, just so that we can get to your answers quickly, because if you're just commenting with your answer, then we lose your answer and it's not considered, and we don't like that. So we like to see every answer. And in case you don't have Facebook, you can answer on pep text, you can email us, and you can SMS us. So you can use every avenue just to make sure that everything is set. Also, people have been asking about this thing right here, which is the Spring School booklet. Remember that you can download it right on the Facebook page, or on the, obviously the link is on the Facebook page, but on the website is where you can download it, and it has all the questions from the Spring School. Use it as your revision booklet, just so that you can be up to date with what we're doing on the show, and you can use it at the end of the year for your finals. So make sure that you get your hand on one of these.
Excellent, Katlego. Good advice. Remember, we're going to be going through some of those Spring School questions again when we do exam school. So if you've missed out at any stage, perhaps you were at school, or there will be lots of repeat opportunities for you to catch up. And we'll also be posting some new exam school questions when they come up, different sections of work that we'll need to be going through. Right, let's get straight back to the KC calculation. I've completed or started to fill in my given information. I just want to go through it with you. I've read off the question that I have 0.6 moles of SO2. So I've filled it in underneath the SO2. Then I filled in that I've got 0.5 moles of O2 and I've got 0.4 moles of SO3. This was at the start. This was where it was previously in equilibrium. So remember, that's what the question said. The system was allowed to reach equilibrium, and it had these concentrations. It then said there was a temperature change. Hold on, there's a stress. So we can start with our initial conditions. Initial means at the start. Now, it said reach new equilibrium, but they found that only 0.2 moles of SO3 was present. And guys, they said they increased the temperature, and we're happy with that. They increased the temperature. We know the endothermic reaction is favored. We know that the number of products is not going to increase. So it decreases, and that all ties up with our theory. It's gone from 0.4 to 0.2. Now, what we need to do, and this is the critical part, you'll notice that I've put down a yellow line in the middle over here. And that's to separate the difference between what we recall the reactants and the products. Remember, these are going to be on your numerator in your KC expression. The ones on the left-hand side, the reactants, are going to be in the denominator. Okay, so how do we go about filling in the rest of the missing bits? Well, it's not too difficult. What we've got to recognize is that if we start with something and we end with something, it's like doing an old-fashioned addition or subtraction sum. What we've got to decide is, do we add or subtract? Well, when it's a product, whatever we started with, we're going to need to work out what's the difference between where we started and where we got to the end. Well, I reckon we started at 0.4 and we've got to 0.2. Well, that means I've lost something. I've lost 0.2. Because you see, what I'm going to do is I'm going to say this number, 0.4, plus 0.2 plus minus 0.2 is going to give me 0.2. So if I lost 0.2 on here, this side, so I have to subtract it. It's used up. Then I'm going to gain on this side. So I'm going to gain something on that side because the reaction is going to favor the reverse reaction. Why? Because we're increasing the temperature. Okay, so be very clear about your signs. Normally, we would just say we add products when we start with no product. We add on the right-hand side and we subtract on the left. It's very important that you see here that we're subtracting and we're adding on the product side. Because this stuff, the 0.2 moles that was SO3, is going to be used to make oxygen and SO2. So let's go and do what we need to do. This is the second critical step, guys. Katlego, we need to make sure that the learners are following. Guys,
Yes.
at any stage, if you don't follow, put something on the page and we'll stop and we'll do it again. We just need to make sure that we've got this step right. When you add up, I hope you can see, to go from 0.4 to 0.2, we've subtracted 0.2. Now, how do we find these missing values? This is the crucial step. Well, it's not too difficult. What we've got to do is we go back to our orange numbers. 2 is to, so it goes in the ratio of 2 is to 1 is to 2. So I recognize that the negative 0.2 is in a ratio with the number 2 there. Okay? Hope you can see that. I've ringed them in orange. What else is a 2 that's in orange? This top line over here, there's the 2. So what I'm saying is if it's 2 is to 2, a ratio of 2 is to 2, that's the same.
Mm-hmm.
Okay? So I guess that what I can do is I can say if it's 2 is to 2, I can write down over here 0.2. Okay?
Yes.
So because this was 0.2, that's got to be 0.2. 2 is to 2 is 1 is to 1. It's the same stuff. Okay? The difference is we're going to add 0.2 on that side. We subtracted 0.2 on this side. We're adding it on that side because we're making more reactants. That's the way the reaction's working. Right. Now, what about this one? Guys, this is where some of you really struggle. And there's no need to struggle because it's really straightforward. How are we going to do it? look at the orange things. Say to ourselves, what do we do to go from 2 to 1? And here you can't add and subtract. You've got to either divide or multiply. To go from 2 to 1, I divided by 2. So to go from 0, 2, now I hope you can see, this doesn't take a calculator or even a degree, but all it requires you to do is to say, I'm going to take this value and I'm going to divide it by 2. I'm going to divide by 2. Why am I dividing it by 2? Because to go from 2 to 1, I divide it by 2. So from 0, 2 to the answer, I've got to divide by 2. And I get the answer over here as 0, 1. And now it makes sense. Let's just check it and make sure our ratio is correct. What's the difference between the 0, 2 and the 2? Well, I could take 0, 2 and multiply by 10 to get 2. If I multiplied 0, 1 by 10, I would get 1. If I multiplied 0, 2 by 10, I'd get 2. Yes, I know it's correct. I've got it sorted. Okay, so a lot of you battle on this line. Once you've got this line sorted, then the KC calculation actually becomes really straightforward. Because now we've just got to do an accounting exercise. What we've got to say is, what did I start with? I started with 0, 5. I've added 0, 1. I'm now left with 0, 6. I started with 0, 6. I added 0, 2. I've now got 0, 8. Tricky step. This is about moles. Guys, we're about 3 marks away from getting the total here. If you get up to this stage, don't throw it away. You've more than got halfway. But what you've got to remember is that this is dealing with moles. And what the KC expression is about concentration. So we're going to add a line that says equilibrium, and we're going to say concentration. And we remind ourselves that concentration is the number of moles divided by volume. And we want concentration or square brackets. So how are we going to do that? Let's go back to the question. If you remember, we read the question originally. It said all of this was placed in a 2 decimeter cube container. So what does that mean? We've got the number of moles. We've got the volume of the container. We're going to say 0, 8 divided by 2. Let's do it over here. Divide by 2 is going to give you 0, 4. 0, 6 divided by 2 is going to give you 0, 3. 0, 2 divided by 2 gives you 0, 1. Now, the last step of the whole calculation, and I've cheated a little bit. I've rewritten my KC, and I'm going to pull it up so that I can see it over here. I'm now just going to substitute these values in, and I'm going to write out my answer 0, 1. Now, look what's happened here. When I copied, it didn't square. Make sure you've got your squares in. So it's 0, 1 squared. The SO2 was also squared. It was 0, 4. 0, 4 squared. And the oxygen is 0, 3. And we answer it like that. And you use a calculator, and the answer that you should get is 0, 21, and that's rounded off to 2 decimal places. Okay, how was that? I hope you've got it sorted out. Let's just make sure we've got the steps right, and if there are any questions, I'll try and answer those now. So guys, first step, go through it. Step 1, write down the KC expression. Step 2, write down the balanced equation. Then you know the form of the table. Write down the ratios. Write down the initial. R stands for ratio. Initial stands for the start. Change is C, and E is for equilibrium. What does that spell? R-I-C-E, rice. Okay? So you can remember the order, R-I-C-E. What are we going to do? Fill in the given information. That's our starting point. Fill in the information at equilibrium. Then do the adding, do the ratio step. Don't forget to divide to give you volume. Substitute back into your KC expression. Yes, you're going to have to rewrite it. Do the substitution and get the answer. And there are your marks in the bag. Ketego, anyone got Comments?
Yes, there is a question, John. This question is by Ntlayiseko Rudo.
Yes.
I have a problem with finding the mole, but given Kc and the mass using the table.
Okay, so in this question, we weren't asked to do that.
Okay.
But let's just recognize something. That table is used when we want to find moles. Okay, what happens if you're given a mass? And I think that might be what she's referring to, or he's referring to. So let's take a simple example, and I'm going to take the example of SO2. And in this case, let's say that they said to us that we were given a mass of, let's make it 48 grams of SO2. That's what we were given at the start. Okay? We were given 48 grams. They didn't tell us the number of moles, and we need to find out what the equilibrium is. We're given 48 grams at the start. So what we need to do is, as I said to you, is we need to get everything into moles. If they gave you concentration, I'll do an example of concentration just now. So what do we need to do? Is we need to convert to number of moles. Always convert to number of moles. Number of moles is the mass divided by the molar mass. Molar mass, look at the periodic table of SO2, and you'll see that sulfur is 32, oxygen is 16, and there were 2 oxygens, so it's 16 times 2. And if you add those two together, you will get 32 plus 32 is 64. So that's the molar mass of SO2, 64 moles per gram. Were we given 1 mole? No, we weren't. We were only given 48 grams. And 48 out of 64, we can use our calculator, which I've stored away over here. We can say 48 divided by 64 equals 48 is 3/4, so 0.75. I'll just check it, 0.75, and there we go. We've got the number of moles. You asked to find the number of mole. You asked to do a calculation. You must find the number of moles first. I think that's it. But let me just do another one. If we were told the concentration, square brackets means concentration of oxygen in this container was 1.5 moles per decimeter cubed. Let's say they gave us something like that. Then what would we do? We recognize we want number of moles. We know concentration is equal to the number of moles divided by volume. Therefore, number of moles is equal to concentration times volume. And in this case, it's 1.5 times a volume of 2, which gives you 3 moles present. Okay. So, guys, that's hopefully the end of KC questions. Practice them. Make sure you can do ratios, and I hope that's helped a lot.
Thank you, John. Guys, I can see your questions on the page. I'm going to squiz them over to John after the break, and we might answer some on the page, might answer some while he's doing the next question. So make sure that you are alert. See you right after the break. Welcome back, Mindsetters. Wow, the interaction on the page is absolutely amazing. You guys are really showing in how much effort that you guys are putting in and how much you guys actually know so that we can actually help you. The questions are lovely. John has gone through them. He will be going through some of them. Obviously, our show is in 2 hours. John, note that down. Next time we should make 2-hour shows.
We'll
just
see.
so that
I might get hung if that happens.
I know, so will our
no.
Mindsetters, but hey, over to you, John.
Thanks so much. Let's go through the questions that we've got. Guys, this was a different type of example, and we've had some key questions about certain stages. And I want to just go over them and make sure that you've got it right, and I will do a second example that I'm just doing here on the spot to try and help you. Recognize the first thing that people have asked is, how did we get that this was a negative? So I'm going to use the white pen here. How did I know that was a negative? Well, guys, look, if we start with 0,4 and we end with 0,2, what's happened? If I have in my hand 5 apples and a minute later, Katlego, I have only 2 apples, what's happened? I start with 5 and I have 2. What's happened?
Someone's taken some away.
Yeah, someone has taken some away. How many did they take away?
3.
3. So over here, I started with 0,4. I ended with 0,2. So what's happened? Something has taken away the missing amount. And that missing amount, remember what we said, here it's decreased. And if I lose something on this side of the yellow line, then I must add it on that side of the line. Okay. Normally, what happens, and I'll just go to the next page and just redo another sort of situation. A favorite chemical equilibrium calculation is for the Haber process. So we'll just write this one up quickly. N2 plus H2 gives you in equilibrium with 2NH3, and we're going to say there are 3 of those. So the ratio here is 1 is to 3. 1 is to 3. 1 is to 3 is to 2. If we say that if we started with 0,2 and we started with 0,4, and that was what we started with, that's the initial. And at the end of equilibrium, when it got into equilibrium, let's say that we had something like 0,1 over here. So at equilibrium, we've got 0,1 moles. We want to get change. So if I started with nothing over there, I didn't have anything. What did I do to get to 0,1? Guys, there's the missing stuff. That's what the change is. This is the line that is really important. So if I started with nothing and I ended with 0,1, what have I done? I have gained plus 0,1. Does that make sense?
Yes, it does.
Okay, so if I gain plus 0,1, remember that this was a product. So if I gain something on the one side, it's like your bank account. If you give me something, then you lost something. Okay? So if somebody gained something, somebody else has lost. So over here, products gained. What happened to the reactants? They lost. So in this example, is different to the previous one. What we know is there was a plus over here, then that means that there must be a minus on this side. Okay. Guys, I hope you've got that sorted out. Remember, you've got to treat these 2 lines as addition lines. This is like one of those old-fashioned things you did in primary school where you were doing addition and subtraction in columns.
Yes,
Eh? So we take these 2 lines and we simply add them together to give us an answer over here. Does that make sense?
That makes sense.
Okay, so I think we've answered all the questions about why was it a negative and how did we get the change? Okay, for the SO3. I just want to go back now to the previous question so that we've got this right. And I mentioned it already, but I want to just make sure that I've answered all the learners who had a problem with the question. And it was about this line here. And I know this is the problem line. First of all, getting that part, and then getting the missing information. So I hope by now we've sorted out just by adding those 2 things together, recognizing if it gets smaller, the bottom one is smaller, then you've subtracted something from it. If it gets bigger than the top, then you've added, and we've got the plus and minus sign sorted out. What's the next step? To get these answers over here, you're going to have to use ratio. I'm going to do it one more time in my example, and let's see if you can work it out with that ammonia example. So here we go. We're going to say, we want to know how much hydrogen and nitrogen I have at equilibrium. What's the change going to be? Here's the key. I must keep things in the ratio of 2:3:1. Now, this ratio is a little bit more difficult than the previous one because this one is just a little bit more complex. The other one was 2:1:2. Here, the numbers will tell you that you've got to do a little bit more thinking. It's not just a case of copy down, but it's not difficult. So let's see. We're going to do it easy first. We always try and look to either get the same or go to 1. So I'm going to say to myself, how did I go from 2 to 1? If I'm dividing or multiplying, I have to divide by 2. So if I'm going to go from 0,1 over here to my answer that goes over there, I must take this number and I'm going to divide it by 2. So 0,1 divided by 2. That's going to be my answer over there, which is 0,05. I'm going to need to subtract that because it was used up. It's been made into something else. Right. Now, how am I going to get from this part here to the 3? What's the ratio? 1:3. Going from 1 to 3. How do I get from 1 to 3, Katlego, if I'm either multiplying or dividing? What do I have to do to go from 1 to 3?
What do you have to do?
I have to go from 1 to 3.
You have to multiply by 3.
I have to multiply by 3. Excellent. So notice that. I've got to take the 0, the answer there, which was in the orange, 0,05, multiply that by 3, and it will give me my answer there, which will be 0,15. I hope that's very clear. Then, to get my equilibriums, I just simply subtract and do the process over. I've broken it down for you, and I hope that makes more sense. Right, there was a question about homologous and heterogeneous. Can you just find that?
Yes,
about the differences and calculating KC. If I remember correctly, I haven't filled them in over here, but just to give you an example with this one, all of these are in the same phase. So nitrogen's a gas, hydrogen's a gas, and ammonia is a gas at these temperatures. That we call a homologous or homogeneous chemical equilibrium. All of them are in the same phase. When things are not gases, then you might have to change the equilibrium expression. So for example, if I had something like this, where I have sulfur plus oxygen, and it is in a chemical equilibrium to give me SO2, and I say that that's a liquid, that's a gas, and that's a gas, then this one is not considered. The information about that one is excluded from my KC. My KC expression would simply be, and it's balanced, so I don't have to worry, would simply be SO2 over O2. Now, there was one other question from Facebook that I just wanted to go through. When you look at your KC expression, I was asked when I wrote this down, why didn't I square the oxygen? Why didn't I square the oxygen? And I thought, oh, I've slipped up. I've made a mistake, but I didn't. Look at your reaction again. And remember, there's your balanced chemical equation. There's your balanced chemical equation below there. 2SO2, O2 gives you 2SO2. There's a missing number there. That number is 1. And that's why that power there is a 1. It's not a square. Okay, so Justin, I hope you've got that sorted out. You understand exactly why the oxygen isn't squared, because we're applying the formula correctly. Okay.
Here's the question, John.
Yeah, sure, go for it.
This question is by Siabonga. He asks, can you ask about homogeneous and heterogeneous equilibria and how to calculate Kc value if we come across it?
Okay, so that was what I just did.
Yeah.
I mentioned over here. This is heterogeneous or heterogeneous. And we exclude if it was a liquid or it was a solid. We exclude it. So then you only deal with the things that are gases or the things that are in aqueous solution. So if you're given a chemical equilibrium and aqueous solution, then you can put that in. We exclude anything that's a liquid or a solid. Those do not form part of the KC. So we don't include those in the KC to get our final result. Okay.
Okay.
I think we've answered those. Guys, here's the last word on KC calculations. If you are struggling with KC, write down the expression, collect your information in the table, and do not spend too long in the exam on trying to figure out the final calculation. Leave it. Work something else. There's lots of other marks on grabs for you. But try your best at this stage. There's still time to conquer this very important calculation. I think I'd like to move on, and I'm going to just quickly go back to a multiple choice question from this paper, and it's one that a region of work that is part of chemical change, but we haven't had much time to deal with it today. So let's go to it. It's that question of redox. And again, something that you've got to get clear in your mind so that when you're faced with it in the exam, you're going to be absolutely 100% sure about it. So 2.7, it says, the gain of electrons, okay, by a substance in a chemical reaction is known as. Okay, now, guys, I know that in everyday language, what happens when we talk about gaining something, then we're increasing. When we're losing something, we're decreasing. Do you know what a synonym for decreasing is? Particularly in terms of people that go on diet. What do? They
lose weight.
They lose weight. They have or interest rate. We have an increase in interest rate or a
decrease
or a
decline
reduction.
or a reduction.
Okay, and that's where it gets confusing,
yes.
Because in everyday life we think about reduction as something that if I reduce your salary, Kat,
yes,
then that means you're going to get paid less. Okay? And that you're not going to be very happy about that.
No, not at all.
But you'd rather want an increase in your salary. But guys, here, what we've got to deal with, we're dealing with chemistry. Chemistry is slightly different. Here about a thought that might help you think about it. We are gaining and losing electrons. What do we know about electrons? Electrons are negative. So if I gain something negative,
yes,
then what would I be doing? Would I be getting more or less?
Less.
I'd be getting less.
Yes.
I would undergo reduction. Okay, so does that make sense? If I gain these negative things, so just think of my bank balance at the moment. I can either gain positive rands or negative rands. If I gain negative rands, what's going to happen to my balance? It's going to get smaller. It's going to reduce. We've got to understand that a gain of electrons is reduction. So with that explanation, I'd like to just add one other thing. Remember in your theory, you've got to have ways of remembering these things. And I've got a couple of tricks that I've learned along the way. The one is an acronym. An acronym or a mnemonic, it means that every letter here stands for something. And oil rig, it's a nice word, we can think about it. Oil stands for oxidation, is a loss of electrons, and reduction is a gain. So what we need to recognize, gain of electrons by a substance is known as reduction. There's no argument about this. Guys, they can get tricky because they can start introducing something called agents, chemical agents, reducing agents, and oxidizing agents. We'll have to speak about that just straight after the break.
Thank you, John. Guys, we're going to go for a break. Of course, as you know, keep in your awareness that there is so much more after the break. So please don't move. And that is also where we'd like to introduce your questions.
Also, competition question after the break. We'll close it after the break.
Okay, awesome. So the competition will be closing after the break. Make sure that you've sent through everything that you need to send through for that competition, including the codes, guys. See you right after this short break. Welcome back, Mindsetters. As I told you before the break, the competition is now closed. What's happening now is that we're putting all your names into like one big giant hat. It's really big. It's like the size of this room. And then we're going to fish out one name for the winner. So keep on your toes for that, guys. But for now, please focus on what questions that you need to send through to us because we're dying for those. Over to you, John.
Thanks so much, Katlego. Now, guys, we've been speaking for a lot of this show about chemical equilibrium, but I do want to deal with a little bit on redox. Just before the break, we started to speak about reduction and oxidation, and I've given you a memory tool to remember what oxidation is and what reduction is. Before the break, I said to you, sometimes they ask these questions about reducing agent and oxidizing agent. Now, today, I don't know if you know, but today is a special day because it's the celebration of a very famous agent. He was given a name in movie history. First time that this appeared on screen was about 50 years ago, 007. So we've got these agents that run around and they do all sorts of things. Well, in chemistry, we also have agents. We have great agents in chemistry. And I want to introduce you to the two agents that we need to know about in chemistry, particularly in the section on redox. So the first one is the reducing agent. And the second one is the oxidizing agent. Now, the agent is going to do something. The agent is going to do something to somebody else. Not so worried about what happens to it or him, but what happens to the other thing. So a reducing agent does something that is described in its name to another object. So if I have a reactant, a chemical, that is a reducing agent, it is going to make something else undergo reduction. Okay? The way that I remember that is I say the reducing agents are really cool guys. They donate electrons. They donate electrons. So we write it like that. Now, just to help me remember that, and to remember that these guys are really cool, I'm going to put the first letters of those two together. And what do I come up with? I come up with the acronym mnemonic that says RAD. And so when we think about a reducing agent, it's really RAD. Reducing agent donates. What about the oxidizing agent? Well, look here. The oxidizing agent will oxidize the other thing. It has to take electrons. And what I remember, how I remember that is again by using the first few letters and saying that we've got an oxidizing agent that takes. So it's OAT. OAT, RAD, and oil rig will help you remember this whole section of redox chemistry. Remember, a redox reaction is one in which electrons are transferred. So something is donating, something is losing. We need to identify which one is which. We apply the theory of these type of reactions to electrochemistry, which is what our next question is all about. So let's just go to it. And here we have the question which says, which of the following statements is true regarding the copper-silver galvanic cell? And that's what we want to know, the true statement. So now, whenever I get something on galvanic cells, I need to remember that these are cells that use chemical potential energy to produce electricity. So they are going to be spontaneous. How am I going to work this out? I'm going to go to the table of half reactions. And I'm going to have a quick look at that table of half reactions. It's very small, but we're going to look on the right-hand side. I've tried to zoom in on it a little bit, and we're going to look for copper on the right-hand side. And the copper that we're looking for is that one there, that copper reaction. It's on the right-hand side. Copper goes to form 2 electrons plus copper ions. And if you look below it, you'll see there's silver. So immediately we can recognize that the copper has a higher, more negative value compared to the silver. So copper as a metal is a stronger reducing agent. It's more eager to donate. So if I have two donors, guys, I have copper and silver, and they both want to be reducing agents. Which one is going to donate easier, more easily, shall I say? Well, it's going to be the copper because it has a value that is closer to 0. It's more negative. The reducing agents are more negative. Reducing agents on the left, on the right-hand side of this table, of this particular one. So copper is going to be the reducing agent. It's more reactive than the silver. Silver is going to have to gain electrons. Let's go back to the question, and now let's see. We recognize that the reaction that copper is undergoing is a loss of electrons. So copper is going to undergo oxidation. We're reading it from right to left, not the normal way. So copper will go from copper metal to copper ions plus 2 electrons, where the silver is going to gain electrons and it's going to form silver. We've summarized the response of what's happening in that cell: oxidation of copper and reduction of silver ions to form silver. Now, let's see what the question actually said and see if we can pick it up from there. Silver is formed at the anode. Oh, okay. So now we've got to do another mnemonic. Guys, we need to know what happens at the anode, what happens at the cathode. Here's the way I remember it. There are two ways. I say to myself, red cat. And what I'm doing is I'm saying reduction takes place at the cathode. I also say that at the anode there is oxidation. The two vowels go together. So if I look at the reaction, I'm going to say silver. I know from when I looked at the table, silver gains electrons to form silver metal. That's not the anode reaction. So that one can't be true. It's not true. This will happen at the cathode. Reduction happens at the cathode. Copper is formed at the anode. Well, guys, we said copper undergoes a reaction in which it loses electrons. Copper isn't formed. Copper ions are formed. So this is wrong. We know that the anode has to be oxidation. And that's not what's happening. Copper can't be formed by oxidation. Well, not in this case. So what do we know here? Silver is formed at the cathode. Hey, look at that. There's the cathode. Silver is a product. I guess that one is right. But let me check that it's not the other one. Copper is formed at the cathode. How do I know that it's not copper that's formed at the cathode? Well, I know that copper is losing electrons to form copper ions. So I'm very clear that the correct answer in this case is C. Now, one last multiple choice question, which is related to this, and it's a very quick one. It talks about an electrolyte. What is an electrolyte? An electrolyte is a solution that carries a charge. So let's have a look at the options. Mercury. No, you wouldn't want to use mercury. Even though it's a liquid, it doesn't have charges in it. We're not going to use molten copper. It could be used in electrolysis, but we're not going to use it as an electrolyte. Dissolved sugar. Well, when you dissolve sugar, there are no ions formed. So it's not going to conduct. It's going to be a non-conductor. No conduction. So it can't be that one. So the only one that will conduct and be useful for us is table salt, which is sodium chloride, dissolved in water to give us sodium ions in aqueous solution plus chloride ions in aqueous solution. And there we go. So table salt is our electrolyte. Guys, those were some multiple choice questions. I think that what we need to do next, Katlego, competition time.
Yes, I think that's about time.
Just so that we can wrap that up, and then we'll take any learners' questions directly after that. Okay, so another multiple choice, but this time one that you've seen, one that you've been working on, and we're asked about the effect of Kc on temperature. That's really what this question is about. How does temperature affect Kc? So I want to explain it like this. I'm going to say to you, we know that Kc for any arbitrary reaction, let's just use a reaction where we say A plus B goes to C. I know that's not a balanced equation or anything, but we're just going to do it like this. We're going to say that's going to be A, concentration of A, times the concentration of B. We'll call these gases, so we recognize they all belong in the reaction, in the expression. So here I've got a fraction. Now, if I've learned anything over the last couple of years, I've learned that most learners love fractions. Kidding. I recognize that most people run away when they see fractions. Yet fractions are part of our everyday lives. We need to make sure that we embrace fractions. Have a love. Hug a fraction today. Get on top of a fraction. Make sure you understand it. Fraction has two parts. First part is called the numerator, the part on the top, and we have the denominator. Now, the numerator, if this is bigger, so let's just get something clear. If the C value here, if this is big, C is big, then what can I say? And I can say C is big and A and B are small. Then what am I going to say? Then I'm going to get the Kc value bigger than 1. If this is a big number, very big number, and this is very small, not the same, but small, make them very small, then you're going to get a value bigger than 1. But if we know that C is small and A and B are big, then we're going to get Kc less than 1. Okay? So make sure that you've got that idea sorted. What we need to recognize here is that it asks us clearly about the value of Kc increases when temperature increases. So it gets bigger. If it gets bigger, that means that the C is getting bigger. That means that we're going to get more products. So in this case, we increase the temperature. We must recognize the forward reaction is favored. We're getting more product, more of that stuff. And we know increased temperature favors the endothermic reaction. Remember, decreased temperature favors the exothermic reaction. So guys, there's lots to think about, but unfortunately, we've come to the end. Hope you've enjoyed today's show. Katlego, have we got a winner?
Thank you, John. And of course, because this is such a great competition, we have a winner, and we have one winner. You today will walk away with 3 CDs, study notes, physical science, and the mindset t-shirt. The winner is, drum roll, John, Ndingi Chiliza. Make sure that you send us anything that you need to send us. I'm going to repeat your name just in case my pronunciation is wrong. And that's Ndinga Chilidzi. Sorry, Ndinga Chilidzi. You are the winner for today.
Postal address, t-shirt size.
That's it. Postal address, t-shirt size. Those are important stuff, John. Thank you so much for joining us today, guys. Remember that there's more shows later. And this will repeat at 4:30 today. Bye-bye, guys.